air interfaces. Air interface is the waveform you transmit over the air. So why is this important? If you look at these use cases we saw, if it was just one type of communication, no problem. You could, and that's what it is today with 4G. It's one waveform, one air interface. But if you want to enable one air interface, that you need to enable applications where you have one particular type of use case where you have large amount of data going to a cell phone, and then you have another use case where it's just extremely bursty traffic, enabling a large sensor network, a massive Internet of Things. This is not large data; it's just very small amount of data, very bursty. Maybe once every 10 minutes, or a sensor sends a signal up to the cloud. In such a case, you want your air interface to be efficient to support this wide variety of use cases. And in the case of critical communications, you want this air interface to be extremely robust. You don't want to lose a packet when a person is being rushed to the hospital or something. So extremely low latency, ultra reliable communication. For those, you want to make your air interface a lot more robust than, say, machine-to-machine communication, where it's a sensor network and it's sending you the temperature of day, every 10 minutes or half an hour or something. So there is a difference in requirements here, which is why they're designing new air interfaces to support these things, to make the spectrum use much more efficient than what it is today. And of course, we talked about this network slicing, and that requires advanced networking features which will dynamically configure the network to support these things. So these are the key technologies that are being used to enable some of the objectives of 5G. Okay? The first one is what we talked about, is additional spectrum. So what exactly are we seeing here? Today, if you think of communications, much of the cellular communications is what's happening in what we call the sub 6 gigahertz band. In fact, it happens to be sub 3 gigahertz. The most predominant use is in the 800, 900 megahertz band, 1.6, 2.3, 2.6 gigahertz bands, and that's where practically around the world much of the cellular communication is happening, whether it is GSM or WCDMA or LTE. That's where it is. Very recently, some countries opened up the 3.5 gigahertz band. Okay? In the US, the FCC came along and said, hey, we want to put this 3.5 gigahertz band to better use, and it's available today. So, and similarly, 6 months ago, there was a ruling from the FCC that opened up bands in the 28 gigahertz band, the 37, the 39 gigahertz band, and also what we call the V band. The E band is another very interesting band which is lightly licensed. And then beyond what we call the W band or the 90 gigahertz band. The interesting thing about V, W, and E bands, there is enormous amount of spectrum, many gigahertz of spectrum. But the problem with those bands is at such high region in the radio spectrum, the signals decay much faster than they decay in the sub 6 gigahertz band. So they don't carry. You need line of sight. They can't penetrate walls, and they're very susceptible to weather conditions. If it starts raining, there is an issue, especially in the 70 gigahertz band, the E band. There is a lot of raindrops and humidity and moisture absorbs the radio spectrum. So when it rains, the signal fades much more sharply. The signal strength drops much more. In the V band, the 60 gigahertz band, there's some phenomenon called oxygen absorption. The oxygen molecules tend to absorb radio frequency signals. They resonate in that particular frequency. So in that particular frequency, you see the signal drop big time. So your range is limited. You are limited to about 100 meters or 200 meters. In the E band, maybe a couple of kilometers is as far as you can go. And even to enable that, you need some very efficient modems, very efficient signal processing to enable that. However, in a situation like this, outdoor shopping malls, large conference rooms, and so on, where your base station is pretty close, can be close, this is perfect. You can offload data to these kind of bands and stream large amounts of traffic over to these bands. So, and that is what 5G is trying to exploit. In fact, they want to intelligently use the sub-6 gigahertz band and these newer bands. You might have heard Verizon is trialing 5G, this year in 2017 and 2018. One of the features is the 28 gigahertz band, and they're enabling fixed wireless access or broadband access to the home with this. And they're not just restricting it to customer premises equipment, but any kind of equipment. It could be your cell phones, it could be your broadband to the home, and so on. And that is in the 28 gigahertz band. Okay, so before we start digging into 5G, I just wanted a quick recap of exactly what is 4G. What is a 4G network, right? The traditional network is something I've shown up there. The connection that the E and B is actually a short form for E node B. That is what we call the base station in a 4G network. Okay. And then at the top of the antenna is what we call the remote radio head. The signal that goes from the base station, the E node B, over to what we call the evolved packet core, the EPC, is a link which we refer to as S1. That has certain properties. It's a carrier Ethernet pipe which is pretty large and can take data from multiple sectors in a base station, multiple carriers over to the EPC. The connection between two E node Bs is what we call X2. And why is this X2 important? Because in the past, this X2 was not there. This was introduced in LTE Advanced and or LTE. The reason for that is to enable much more efficient handoffs. Instead of going from the traffic going from the E node B to the packet gateway to the EPC and back to the new base station, this shortcut, this short link can transport whatever is needed as a cell phone is moving from one base station to the other, and that link is called X2. The PDN gateway, or the packet data network gateway, is your window into the internet, is the connection between the radio access network and the Ethernet, the internet, the broad internet. The serving gateway is the kind of the dual of the packet data network, and it's the gateway towards the radio access network. The HSS is what we call the home subscriber server, where that has the list of every single subscriber, and it knows what your data plan is, whether you have a $100 data plan or a free data plan, and this is basically used to give you the kind of service you have subscribed for. And the MME is the mobility management entity which keeps track of which base station is supporting a particular user at any given time. So as a user moves around, it gets updated in the MME. He goes from base station to base station as the handoffs happen. The MME is what is updated. So that is sort of the core of the packet network. What is shown below is the new architecture, what we call cloud RANs. Right? These are the two extremes that we are seeing, where processing is happening all at the mast, at the bottom of the mast, in the case of the traditional network, towards this new thing, the other extreme called cloud RANs, where much of the processing now has moved into the cloud. Right? So instead of each base station having its own dedicated processing, all of that processing moves into a pool, which we call the BBU pool. That is sort of your, kind of your aggregation unit, which brings in all the signals, raw signals from the antennas, and processes it in these centralized or data center-like units. It could be a centralized RAN or a cloud RAN, as the case may be, as the features that are enabled by the cloud are used or not. So those are the kind of connections that is happening, the big connections that you can think of in what we call a 4G network. The cloud RANs are fairly new. I mean, there are a few cloud RAN deployments. There has been a bunch of work that happened, but in 5G, this sort of technologies will play a much bigger role, and the network will change in a much different way, and the splits and the movement of where processing happens is also changing. Perfect. Oh, wow. Okay, thank you. So to give you an idea, what exactly is happening, right? So this was your traditional network. We moved all of these processing over to the, if you move it over to the EPC is when you get the Cloud RAM. If you move some of the processing over to what we call the PDCP aggregation node, instead of L1, we have L1, L2, and L3, different layers in the baseband chain. Some portions of L2 and L3 are aggregated in this PDCP aggregation node. And then this aggregation connects to the EPC. This is one architecture that's happening. This enables what we call the edge cloud, or you might have heard of another term called mobile edge computing. So this is sort of the enabler for those sort of things. The PDCP aggregation node could now be merged into the EPC as well. The other thing that we have is the E-band, V-band converged access and backhaul. So if you now look at the spectrum in the 70 gigahertz and 60 gigahertz band, you have a large amount of spectrum, but do you want dedicated backhaul and dedicated access, or can you combine them? You can use beamforming antennas to deliver signals to a particular user, and then you can point the beam another way and use that as a backhaul. So those are technologies that are being explored right now. And then we have the 28 gigahertz band, which enables fixed wireless access. That's what we talked about. Broadband access to the home, all interconnected in this whole radio access network. What this means is the baseband as we know it needs to split, and it needs to split in multiple different ways. Okay, so and that is kind of the graphical view here. This is 4G, where you have the baseband and the MAC layer, as they call it, at the bottom of the mast, the remote radio head or the digital front end up near the antennas, and then the analog front end also up near the antennas and signals going out. Now to enable some of these massive MIMO and those sort of functions, some key technology is moving from the baseband at the bottom of the mast, or maybe it's in the cloud now, over to the DFE. So the lower PHY is one candidate for moving, and some people consider the entire PHY to move up to the antennas. That's also under consideration. And then there are other forms of integration where maybe you have DAC and ADCs integrated into the same unit that provides the digital front end. Okay. So all of these things, what the point here I'm making is the complexity of the remote radio head increases. And this doesn't mean the complexity of the baseband decreases, because now you are processing significantly large number of carriers or large number of antennas because of massive MIMO and so on. So it's not like the complexity of the base station is going down, but it's just that the complexity now is being redistributed between the baseband and the remote radio. Now these are all the different functional splits that are being considered. This picture is directly taken from the 3GPP TSG RAN standard, that a document that's out there, with splits being considered from option 1 to option 8. The popular splits though are split 7, where the lower PHY moves to the radio. We see that happening. And then split 2, where we talked about this PDCP aggregation node. So this brings us to the idea of, some people call that mid-haul. Although this mid-haul is a term that's kind of evolved, is just, you hear it in the last couple of years. So you have the front haul, which transports traffic from the baseband to the remote radio head. The mid-haul to enable this PDCP aggregation node, and then the backhaul that takes signals back to the base station. So exactly what is front hauling? Right? Front hauling is the transport of IQ signals or modulated signals from the baseband to the radio. Now, if you think of your Wi-Fi system today, in that one box, you have the baseband and the radio, all of them integrated. In fact, in some cases, they may be integrated on the same chip, on the same device, then going off to the antennas. But here, what we see is the baseband split and the radio up at the antenna. In the case of cloud RANs, there may be a separation of a couple of kilometers between. So that's sort of how different these systems are. And this particular IQ signals is what we call front haul. The back haul is more Ethernet traffic. It's just payload. It's just bytes and bits going back to the EPC. The CPRI, or the Common Public Radio Interface, is a popular standard for transporting IQ signals. Then one of the most important things is the frequency and timing between these elements are extremely critical. Okay. So here is a quick note on the math around how far the remote radio head can be from the baseband. In fact, it limits the distance your cloud RANs can support. Right? Quickly, you see that the distance now is limited to between 15 to 20 kilometers, and some people are conservative and say, hey, no more than 5 kilometers or no more than 10 kilometers. But this is your upper bound. Okay? And I guess these slides are available later on, right? So I'll skip these in the interest of time. Okay. CPRI is basically packing these modulated IQ samples into what we call one CPRI frame. There are many ways of doing it, and the intent of doing it this way was to enable different radio air interfaces as they evolved. Going from GSM to WCDMA to LTE, now LTE Advanced and 5G. They all have different rates, they all have different number of bits and so on, and CPRI tries to pack it as efficiently as possible and tries to multiplex it with timing and synchronization signals to enable the whole network to stay together. Okay. So this is basically again some fundamentals of CPRI. It supports a whole lot of different line rates, and as the traffic drops during the nights or so, you can save energy by kind of dropping the rates, going to lower and lower rates, and sometimes you could even provision it with lower rate connections. So that's kind of the support here, different rates. And the reason I put this Ethernet here is because the next generation of 5G traffic is going to be on Ethernet, which is what we call radio over Ethernet, and that's kind of what Carrie was mentioning with what we call eCPRI, the next version of CPRI, which also transports traffic over the Ethernet. And the rates that are being under consideration are the 10G and the 25 gig Ethernet. Okay. So, what is the big change now in the front haul? We talked about, in a couple of slides ago, I mentioned the packet core changed from circuit switch to packet switch in 4G. So now the front haul is going from a tight fixed circuit or hardwired connection to a more of a packet-based connection, a dynamic changing packet-based network, a configurable packet-based network. Now this is a big change. You can think of breaking up your communication system into two parts, and these two parts are now connected by a packet-based, Ethernet-based system. So, is this really possible? Well, there have been some studies and so on that people have done and figured out, if you make these kind of changes, it is possible. And one of the big things to note is Ethernet is a best effort delivery mechanism. It's not meant for bounded delays or low latency communication. And the changes that need to happen are basically under what we call, are underway, and Ethernet is in fact changing from this best effort delivery model to what we can call a deterministic Ethernet with bounded delays. And this is the topic of a new standard that's being worked out by IEEE called the 802.1cm, or the time sensitive networking for packet-based front haul. And you can, if you just Google 802.1cm, you'll see all of the documents and conversations that are happening in that particular standardization body.
We'll probably have a room on BRAX as far as to cover topics like that. So that's the nice thing about the 5G tech community on BRAX, is you're going to have rooms with all the different places that you can get updated information a lot easier than you can search. Okay. Good information, thank you.
So this is the, just a big picture of the packet-based front haul with the remote radio unit, the signals that are close to the antenna sitting there. And then you could have the baseband unit here, and then the packet core as part of this overall bridged unit. And now you have Ethernet switches all the way through, dynamically being configured to route traffic in the best way. Okay. And one last slide before I move on from this topic is exactly what does it take to enable this kind of bounded delays in a deterministic Ethernet. The key technology is what we call frame preemption. If you have a large frame that is being transmitted, and you have to wait until that entire frame goes through to let your front haul traffic go through, right there is delay. You've already violated your delays and latencies and whatnot. So one of the things is frame preemption. You stop that frame and you let your express traffic go through, which means you need to have two MAC layers, one for express traffic, one for preemptible traffic. And then there is this MAC merge layer that takes care of merging and so on. So this is one of the things that is already part of 802.1cm, and then there are other things also that are in consideration, and that standard is evolving as we speak. We are at draft 0.5, just to give you an idea of how early in the draft it is. Okay. So these are all the bricks that make up the front haul network. You have 802.1cm, and then you have what we call eCPRI, or the encapsulation layers on top of it, and so much for front hauling. Now you might say, what exactly is it with FPGAs? And the key thing is, these FPGAs provide the right resource mix to enable front haul systems. They have high-speed networking, up to 32.5 gig, even 56 gig transceivers. And then you have programmable logic. You have lots of memory, processing horsepower, and so on to enable high-speed or efficient front hauling. In fact, it's a very, very integrated system. You can build large front haul switches as well, as you switch data from one thing to the other, one antenna to the other, or you can enable large Ethernet switches or time-sensitive networking switches for front haul. Okay. Yeah, I'm almost done. So this defines what exactly is at the foundation or the heart of an FPGA. You have what we call configurable logic that can be configured on the field on your desktop. Then you have lots of memory. Then you have all sorts of IOs that are available for you to program your stuff. Every design uses memory, and there are many different types of memory available on your FPGAs, and some of these are critical for you to enable front hauling. Okay. There are different type of switches you can build, and this sort of configurable logic makes it very efficient and cost effective and power efficient to build these kind of switches. Okay. One of the types of block RAM or memory is called what we call block RAMs, and these kind of hardened cascades allow use in practically every sphere of technology, whether it is terabyte OTN switching or 800 gig data center interconnects, mobile backhaul, the cellular access, test and measurements, video conferencing, and so on. So lots of different places, and also in some broadcast cameras and even some of these advanced consumer electronics and automotive